For our project, we decided to explore an emerging product category rather than one that has been well established. We chose a tabletop injection molding machine, which is used for small, low-scale injection molded parts from plastic chips. The user inputs the material into a funnel, which liquefies it via heating elements and feeds it into the mold via a leading screw. Once cooled, the mold plates separate, depositing the finished part. Currently, the annual production volume of these machines are limited. However, there is a large potential market, considering that there are almost 1 million desktop 3D printers sold in only the fourth quarter of 2023. We believe that the market size for this product is well above 50,000 units per year. The primary customer base is at-home hobbyists that want to create injection molded parts at home for their personal use. The secondary customer base are people who want to recycle plastic by creating filament for the 3D printing process.
Here are the three views and the isometric view of our injection molding machine. The next slide shows all of our 24 parts and sub-assemblies shown in the exploded view. And then we have included our bill of material on the left with number of parts and assemblies shown on the right. For the bill of material, we have included all the parts and sub-assemblies, and then we calculate the total unit cost of each part. And the total cost is $1,133.3. Noted that the product is available online at $6,500.
Here we have our functional analysis or FAST chart. The primary function is to create a part with its supporting functions shown in later branches, notably containing plastic, heating plastic, maintaining the temperature, moving plastic, maintaining the shape and pressure of the part, cooling, creating a gap and breaking the adhesion, and for the user, protecting hands, insulating heat, and ensuring repeatability.
For this first fishbone diagram, you take the frame and kind of build off of the frame. So you add the stationary plate, the rail, the different belts and motors, and you install them onto the frame more as parts. In the second fishbone diagram, you take the frame, but you take other larger sub-assemblies and attach them to the frame. So the whole assembly is assembled more in parallel with different sub-assemblies. To compare these sequences or fishbones, we use criteria to determine which one is best, and we found that sequence 2 or fishbone 2 performed better as it's assembled more in sub-assemblies.
Our function component mapping matrix shows the various functions with all of our parts from our BOM. Notably, a lot of parts are involved in moving plastic, maintaining shape and pressure, breaking adhesion, creating a gap for the part, and also ensuring repeatability.
For our functional differentiation table, we have two columns, one which is the same for both customer groups and one which is different for each customer group, and our differentiating factor here is moving plastic, which is dependent on the variant. Then we have our component commonality table, which has a platforms column and a modules column. The modules column and platforms column map back to the function component mapping matrix, with the modules column being all of the things dependent on the move plastic and the platforms column being generic for both customer groups regardless of the variant. Next we have our common interface. This is the stripped down version to which parts can be added to create both of the different variants.
Our quad chart shows the intersection of functional importance and manufacturing and assembly costs. Notably, the high functional importance and high manufacturing costs and assembly costs are candidates for DfM and DFA.
Here we have two of our main variants for this injection molder. On the left, we have the main one that we've been talking about this whole time, that uses the two colliding plates to create a mold and feeds plastic into it using an auger. On the right, we have a similar feed system, changing the extruder nozzle for a 3D printing filament size that feeds onto a motor-driven filament spool to recycle plastic into future 3D printing filament. On the next slide, we have our visual assembly diagram, where we can see that we do split at those extruder nozzles, since those will have to be different sizes for the two variants, which we can later change on the next slide to simplify out these two variants and how they're built, mainly separating out what's in the right side of the frame.